This video is titled Energies of Atoms in an Ideal Gas. Why am I going there? Well, we wanted to talk about atoms. And if we just want to talk about individual atoms, an ideal gas is a good choice. Okay, how do you get an ideal gas? Well, the first problem is there is no such thing as a perfectly ideal gas. An ideal gas is a gas where each atom is completely independent of one another. The atoms can collide with each other, but there are no special forces between those atoms. A good choice for something that's close to an ideal gas is helium, might be a good one. Uh, Neon might be a good one. Let's just say we're going to use helium. We're going to use helium. And what's helium? Well, it's got atomic number of 2. And that means there are 2 electrons, 2 protons, and usually 2 neutrons. It just depends on the isotope of that helium. Now, that might be more information than we really need, but I gave it to you anyway. What affects the energies of that helium? A good measure of what the overall average energy of that helium is the temperature. Temperature in science, in physics, and chemistry, the best measure of temperature is the Kelvin scale. Kelvin 0 means no molecular activity. Kelvin 273 is the same as the freezing point of water. So, most of our measurements would be, or most of the experience of that helium would be above that freezing point of water, and room temperature would be, that'd be about 293 degrees Kelvin. Each step of the Kelvin scale is the same as the Celsius scale. The Celsius scale is 0 at freezing point and 100 at boiling point of water. So there's 100 steps between freezing and boiling. The same distance of that step goes all the way down to 0 Kelvin. So we borrow the steps from the Celsius scale and adapt the numbers of the Kelvin scale to go along with that. Getting a little off track here, but the thing about these videos is that it's the way my mind happens to be going at the time. Now, the title was Energies of the Atoms in an Ideal Gas. Let's say we've got this helium gas, and it's at room temperature, or maybe a little bit above that, and let's just call it 300 Kelvin. Nice number to use. Now, if it's 300 Kelvin and that's related to the energy, then does that tell us that the energy of those atoms is all the same? No. There's going to be the probability that Some atoms are much higher than others, and other atoms are going to be lower than others. More probable is that atoms are going to be at lower energy levels than higher energy levels. All of this is leading up to a concept of probability and energy levels. And when we get done with this, if I'm doing this correctly, we'll have some numbers that we can throw out there and come up with probabilities of these energies with some numbers attached to them. And with this numbers that we attach to them, that will give us some statistics. In other words, kind of come up with the numbers of how many atoms are at one energy level versus other atoms at other energy levels. And this is getting a little goofy as I'm listening to myself talk right now, but the whole idea is to come up with an expression that helps us explain the energy levels, and eventually it'll help us explain characteristics of atoms themselves.